So then we have the next speaker, which is Hugo Dev Lenovel. We'll talk about enhancement of FRL08, methodological connection between simulation, experimental, and utilization of AI tools for coincidence matrix analysis. Please.
Okay, hello everyone. I'm pleased to present our work on enhancement of our certified laboratory. So this study focuses on methodology, Monte Carlo simulation, and data analysis for coincidence measurement in nuclear test monitoring. So the CEA for France contributes through the development and the deployment of a radio xenon station called SPALAX and SPALAX-NG, and also operate a certified laboratory responsible for sample analysis. And this laboratory uses advanced systems like the Gamma Cube, which combine 3 HPGA detectors with an optimized shielding for high sensitivity measurements. And our research aims to improve coincidence measurement to better detect and interpret low level of radioactivity. So simulation is central to this approach, as it provides detection efficiencies when experimental sources with all the radionuclide of interest, for example, with the relevant list of the CTBT are difficult to obtain. And we create our model from manufacturer drawings and also radiographies. And we select a radionuclide covering a wide energy range, and the metrological connection is made with calibrated standard sources in multiple geometries, ensuring applicability for new setups. For example, with the new geometry RASA 2. Optimization and validation comes. How we validate our model, the key parameter is the detection efficiency, and we adjust some physical parameter until the ratio of the experimental to simulated efficiency is close to 1. And we define 2 criteria to validate our model. The first one is a mean ratio deviation between below 1%, and the second criteria is an expanded standard deviation below 20% at low energies and below 10% at higher energies. And once validated, this deviation defines the model uncertainties, giving reliable precision. So the method we propose calculates detection efficiency through simulation for activity determination. And for coincidence measurements, we simulate the coincidence spectral signature from an extension of the MCNP code. And this method has been tested on 2 experimental configurations. The first one is for radioxenon isotope sample, and the second one is for particulate filter. So the first validation is with a gaseous sample. So we used a PIPS box placed between 2 HPGA detectors, and we use also the region of interest method to quantify activities. Each radioxenon isotope was assigned a region of interest, and efficiency were derived from simulation, as you can see in table 1. And I present our results in table 2, and it shows excellent agreement between measured and reference activities, confirmed by a normalized deviation score. And this validation led to a publication. We now turn to gamma-gamma coincidence with a particulate filter placed between 2 HPGA detectors. So this technique already has strong qualitative value for confirming radionuclide, for example, with the cesium-134 that emit cascading gamma ray. And for example, during an intercomparison exercise from the CTBT, we confirmed the presence of cesium-134, which was difficult to identify with classical gamma ray spectrometry due to interferences between radionuclide. But when we conduct coincidence measurement, we can see a clear signature from the cesium-134. For activity quantification, we tested our method on a swipe sample from the agency. We also used the ROI method, and we determined detection efficiency with the simulation. And here you can see our results. As you can see, uranium-235 was present only in trace amounts, and gamma-gamma coincidence effectively confirms such low level of radionuclide. However, gamma-gamma coincidence matrices are large and time-consuming, and to address this, we propose to develop artificial intelligence tool for qualitative detection of radionuclide. So the first step is to build the database, and more precisely, the first step is to reduce the size of large coincidence matrices. So we removed unused pixels and flattened them. The database includes both single radionuclide signature and fission products distributions. And we also added random distribution with uniform distribution and bimodal distribution to ensure a full coverage and to see all the radionuclide that can be encountered. For the AI model, we choose a convolutional neural network, as spectra can be treated as images. The network extracts local features first and then global pattern as we go deeper in the architecture. And the final layer are fully connected and perform multi-label classification, deciding if radionuclide is present or not. For the model evaluation, we first visually inspected the raw output to check the separation between positive and negative events. So, as you can see, for the cesium-136, we have a very good separation between positive events and negative events. So we can therefore assume a threshold close to 1, and if the raw output is above 1, we can consider that the cesium-136 is present. And but for the tellurium-129, it's impossible to assume a threshold. In practice, this threshold is determined with the precision recall curve. So the precision and recall depend on true positive, false positive, and false negative, and we determine F1 score with as an harmonic mean of the precision and the recall. And it's possible to obtain a precision recall pair for each threshold. So we obtained this curve by using different thresholds and determining different precision recall pair. And the F1 score sets, and the best F1 score sets the optimized threshold, balancing sensitivity and precision of our model. Overall performance is measured by average precision, recall, and F1 score for all the classes. And as you can see, the overall F1 score remains below 80% because weak classes are included, but in practice we can ignore them. In testing, we applied our model to a standard source with 10 radionuclide, but only 4 radionuclide can be detectable by our model. And if the predicted probability is above the threshold, the radionuclide is considered as detected. So the model correctly identifies 3 out of 4 radionuclides with activity of a few hundred becquerels. And the detection, my opinion is that the detection of cobalt-57 was difficult due to low energy signature. The model also performed well in an intercomparison exercise. Most detectable radionuclei were correctly identified, and manually we detect ruthenium-106 and cesium-134, and our model detects one of them and ignore the other one. But it's importantly to note that we don't have false positives, so it's interesting and important for us. In conclusion, we made the metrological connection with Monte Carlo simulation. Simulation-based method accurately determine detection efficiency both for both for standard gaseous sample and also for particulate filter. We also developed a convolutional neural network to classify radionuclide. And in future work, we plan to refine both the database and the CNN architecture to better detect radionuclides. And we also aim to test a spectral unmixing algorithm developed by Charles-Philippe Manot. I encourage you to see his poster tomorrow. And we want to compare this method, our method with artificial intelligence and the unmixing algorithm. Thank you for your attention.
Thank you very much. So, questions, please.
Thank you very much. Interesting. So, you mentioned that you did a test with 4 nuclides, one of which was failed to detect was cobalt-57. My question about this is, what was the challenge? Would a human analyst easily have identified cobalt-57, or was it at close to the critical limit, or is it simply that the method is unable to identify the nuclide at any number of counts? Can you describe that a little bit more, please?
It's about the detection of cobalt-57 with the AI. Yes.
Yes. When you mentioned that the CNN fails to identify the nuclide, would a human manual analysis have found it, or?
It's difficult to see this radionuclide because it can do a coincidence with 14 keV with 122 keV. So manually it's also difficult to analyze.
Have you compared with some other method like peak coincidence, just the region of interest around that?
Yes, but the coincidence is not very important, so it's difficult to analyze, and it's difficult to say what the CNN see. So I don't have more information.
Thank you.
Yes, please.
Thank you for the presentation, Hugo. I have a question related to the computational resources that you need, because you mentioned that kind of HPC, you put a picture there. That was for training, but to run your methods, do you also need
No. To run the model, you need a PC, and it's okay. It's just for the train, yes, the HPC computer.
Okay, thank you.
have an online?
No.
No. More questions? No? Okay, thanks again.
Thank you.